For Deaf. So our speaker today is Jesse Thornburg. He graduated from MIT in 2011 with degrees in mechanical engineering and comparative media studies, and he's now pursuing a PhD in electrical and computer engineering at Carnegie Mellon University. Since graduating from MIT, Jesse has spent 2 years in East Africa, specifically in Rwanda and the Democratic Republic of Congo, developing and managing hydropower plants, implementing water filtration projects, and planning food and agricultural distributions in a war-torn region. So today, we'll discuss carbon needs in East Africa and how engineers can meet those needs, all through the lens of his experiences there. So I personally had the privilege of meeting Jesse at a conference earlier this summer, and we're actually very fortunate to have him here. So please, everyone, give a warm round of applause.
Thank you very much. Really thankful to be back in the U.S. and especially here at MIT. And as Sammy said, I'm going to discuss some of my work over the past 2 years and how that's informing my current PhD. This won't be very technical because of the nature of the work. As Sammy mentioned, there's just so many various responsibilities to get anything technical done in this region there isn't, at least with the current climate, there's not much research or technical innovation going on aside from the day-to-day innovation of can we do a first world job, solve problems with very little resources. So first I'll talk a little bit about the region, and then about micro hydro, run-of-the-river hydro for those who might not be familiar. And then I'll go into my work, how I ended up in Africa, from here, some engineering work in industry around Boston, and then Democratic Republic of Congo, and then Rwanda. Finally, talk about some other opportunities in East Africa, and challenges, and then my current research as a PhD student. So I'm not sure how much many of you know about Africa, but this sub-Saharan region is the central and eastern part, very fertile, jungles and Serengeti. The area where I was based was just at this juncture of Rwanda and the Democratic Republic of Congo. I lived for a year in Goma and a year in Rwangari in the northwest of Rwanda. This juncture of Rwanda, DRC, and Uganda is the only place where mountain gorillas live. So if you've heard of Diane Fossey, all her expeditions were based there. And for the past year I've lived in the town where she was based. And that's really the main economic driver of that region, is tourism. And if we can call it an economic driver, aid money. Still 40% of the Rwandan GDP as a country, 40% is aid money. And they actually brag about that because it's much lower than the percentage for the surrounding countries. I should also, just to, on that note, the gorillas are here because it's an area of high mountains, volcanoes, where it's very fertile, where literally you can take a branch that's been freshly sliced from a tree and stick it into the volcanic soil and it will grow a new tree. My neighbors and coworkers would do this when they visited. When they saw a new tree, visit somewhere, they would cut off the branch and take it back home. And that really informs the culture of this region, that it's very easy to get food. It's very easy to survive, and so there's often not seen a need to thrive or build something sustainable for the long term. First of all, Democratic Republic of Congo is a very large country, about a quarter the size of the U.S., and very poor. Let me go back. That's this entire country, and there are actually no passable roads through the center jungle. So if you wanted to get from the east where I lived to the capital, Kinshasa, you would have to go through either these surrounding countries, Central African Republic, and others to this point, or to the south. So it's, yeah, and the government is all on the west coast. The east is hardly monitored. The east is also the location of 60% of the world's coltan, which is used in silicon chips in every smartphone. That eastern region is also where they have diamonds, oil, and gold. So it's constantly a target for illicit mining, for smuggling, and from that, you know, comes child slavery and trafficking and things. So if you've heard of Joseph Kony and Invisible Children, they were in Uganda at first, and then were in Democratic Republic of Congo for a long time, and now are up in Central African Republic. That's Democratic Republic of Congo. The conflict there is largely because of the minerals, but it largely started because of the 1994 genocide in Rwanda. So the conflict there, as you probably have heard, was between the Hutu and Tutsi tribes. Rwanda is unique in the region in that it is almost entirely made up of only two tribes, and they speak the same language, which is really unusual in Africa, where DRC you have hundreds of tribes with hundreds of different native tongues. Rwanda, you have two tribes that speak the same language and really had different roles in society, so they were constantly at rubbing, how do I say it? There was constant friction, and it exploded from the 1960s up to 1994. Now there's a stable government, which is very clearly a tyranny, but seemingly the tyrant is beneficent, so we're crossing our fingers for the next election. So anyway, a difficult place to work. Because it is mountainous with rains pretty consistent year-round, even in dry season you don't have drought or famine in this part of Rwanda or Democratic Republic of Congo. So hydro is really perfect. Hydro is an established technology that doesn't take the precision or technical training of some other energy technologies. So if you visit a big dam, you're going to see something like this, where they have created a reservoir, and then below what you can see, they have a pressurized entryway, penstock or pipe, going to a turbine. Sometimes it's vertical axis, sometimes horizontal axis, that turns a synchronous generator, and that generates power in 3 phases, which is then stepped up to a higher transmission voltage. Now, a more recent version of this that's been largely pioneered in the Himalayas is, instead of damming up the region, especially if you have a small amount of water anyway, or you need to leave water constantly flowing in the river, you can just create a raised barrage weir that doesn't block off all the water. It lets water flow constantly, but it diverts some of it into a canal, and then you send that water from the canal into a pressurized pipe, either above ground or buried. And in this turbine house is a similar setup, where it's spinning a turbine to generate power with the synchronous generator. In both cases, the water goes back into the river at the end. Most of the innovation, I guess most of the published work I see is for these more standard hydro plants, because there's a lot of worry about, you know, fish getting up and down river. There's a lot of worry about air getting sucked up, cavitation that damages the turbine. So anyway, this is much more profitable, I would say, because it is a technology that serves so much of you know, the electric grid globally. Whereas this is smaller, a few companies do it well, but it's not, yeah, like I said, it's something that is easy to set up wherever you are with pretty minimal technical education. So I had no education in hydro, no background in it. Here I studied mechanical engineering, and very soon after declaring that as a major, I moved more into robotics and controls. So I was doing Europe's in Sea Sail and in the Sea Grant AUV lab. I was telling Sammy that yellow submarine robot is very familiar. So I while at MIT worked on this little submarine robot with that lab. I also had an internship in Guatemala where we were, I guess in name we were fixing and installing solar panels, but a lot of the time we were kind of doing hippie, like sustainable housing projects. And after I also during my MIT years worked an internship at the DC subway system. So vehicle engineering, you know, I guess that's your standard like stresses and strains. Out of college I went to iRobot just north of Boston and worked on the Roomba robot vacuum and on military EOD disposal robot called the Sub-V. And from that cubicle in Bedford, Massachusetts, I kind of realized that the entry-level mechanical engineering position wasn't where I wanted to spend my next few years, and even when I moved up, it wouldn't be it wouldn't be the work that I wanted. It wouldn't affect the people that need engineering in the way that I was starting to see it. So that's why from iRobot, I applied to different NGOs and talked to different connections in Africa. I had visited Malawi for a few weeks in high school, and so had this vision of, hey, there are real engineering needs in Africa, and I was pretty useless to serve those in high school, but maybe now with a mechanical engineering. So I applied to one NGO called World Relief that had a need for an engineer in the Democratic Republic of Congo. So I went to this project that basically most of the NGO knew about it was this turbine is broken, and it was made in 1929 in Ohio. It ran until 1957 in a municipal Ohio, or I think actually Oregon, hydro plant, and they decommissioned it because it was old and outdated, and they sold it to missionaries for $1. So this is the missionaries installing it. This guy, there are two different pictures with kids, and one of the kids hasn't been established which is now an old man who advised me on this project. He's now an engineer. So anyway, back in like the late 50s, they built this small dam, you'll see it better in the next slide, and dried out this region below the river, and they installed the turbine there, which you'll see better in the next slide. And it's been running essentially ever since, though from the 90s to the late 2000s, it was very sporadically in operation. 150 kilowatt capacity, though I think that turbine was slightly undersized, so it only got a maximum of 125 kilowatts. Here's the actual turbine blade when I arrived. You can see this one's broken off. These had actually been welded back on locally, which I'll just say that hydro turbines have very specific and optimized curves for their fins, and to make one yourself with, I guess, without a CFD background or without an understanding of flows is not going to be efficient at all. They had done that many times with different blades, and they had finally given it up. Here's the hydraulic control system that would open. Basically, this is directly below this circle, and they would open and close gates to let water in and out. But as I went around the powerhouse and tapped on different moving parts, rust would just fall off them. So basically all unusable except for that dam and probably the powerhouse, but they had no tools to take measurements or establish are these structurally sound now? What were they built to any standard? So anyway, it's an area of the world where if you want to go there, you have to be ready to tackle, you know, any new problem on any given day, and you're gonna meet resourceful people like the people that did take this out. So I think when they removed this to weld back on fins, they couldn't even dry it. They weren't able to dry this out again, so they were actually like swimming as they pulled this down and out, and a guy nearly drowned, and it was just, yeah, bad situation. But they make things happen. Also, a local technician trained as a diesel mechanic had created a whole new like cooling system and control system in the powerhouse. So you see, I would say very entrepreneurial people, but it's always for a very specific task. And once that task is done, there's very rarely an attitude to productize it or expand it into a business. More it's, okay, I've solved the problem, it's running, let's go back to how we always were. Now I know I'm making some generalizations here, and those are based on my experience, but I don't want to imply that all the people of DRC or Rwanda are like that. But no matter what you read, you'll find there are some attitudes of fix it to be good enough, and then go on with life as it was. So I went from that. That was 1 year. I didn't even mention the real limiting factor on this project was right after I heard about the position, a rebel army took over that project. So to even visit this, get these pictures and take the civil measurements, make the plans I did make, I had to meet with the rebel leaders and get their permission to go in to this project. So for that reason, the funders that we had to cover the cost of, it wasn't even new equipment, this 820,000 is for refurbished German equipment that would be a new turbine, generator, transformers to stick into that 1950s powerhouse. But we had that covered by funders with sort of a, energy grants and carbon credits, and they pulled out when the rebel army took over. And I understand it, but it's something I didn't expect to be a challenge, you know. So I raised more funds for this project during my time there, and when I left, they had the promised funds to build it, but the rebel army was still in power, so they couldn't build it yet. And they basically said to me, you know, you signed on for a year, we don't have other work for you because the rebels are still controlling this, so we can't offer you anything more. So I went to a startup in Rwanda that had just finished constructing this scheme. So this is the second, I guess what we just looked at was similar to that first type of scheme, where you do have a dam and a small reservoir. This is the second type of scheme, where we have a canal up here and a small dam 1.5 kilometers up the river. And then you have a 100-meter pressurized pipe going down to this powerhouse. This one is a horizontal axis turbine. This sort of turbine is similar to a water wheel on a riverboat, and it's in line with a gearbox you can barely see in gray, a flywheel, and synchronous generator that sends out power in 3 phases. So this is a German machine. Here's the runner, the turbine that's similar to a water wheel. And so I managed this plant for a year. We sold power to the Rwandan national grid, and it's such a small country that their whole grid is run by one utility. That's, I get, it was federal when I started, and then they were transitioning it to be partly private, partly federal, and it was very corrupt, and then now it's fully private. So, but it's still a single utility. 438 kilowatt capacity. This is an area where they now have available low watt bulbs of about 10, 15 watts. So that means for a house to have 1 or 2 light bulbs is the big step up, and that's what most houses want. So this actually goes a long way. 25 local staff. I was managing My boss is actually a TPP grad and also PhD in course 1, who had studied who had done some optimizing of hydro projects during his time here at MIT. But he was really focused on some future projects that haven't yet come to fruition, where my main focus was this one. We've had a lot of wear on this. We had to do some mitigation, because there was a lot of sediment in the water. I just kept finding issues that hadn't been planned for in the design. So like I said, not much room for innovation and new groundbreaking research, sadly. These are some challenges that I found. If you're interested in working in this sort of environment, just be ready for scarcity of resources, and what's more disturbing is that everyone is okay with that fact. There's no real attitude of, like, we need to get good tools or we need to have standards. It's more just throwing up our hands and saying, well, we can't get that tool except in South Africa. And yeah, the big push, the country is very organized and well run in terms of getting kids to school. You still see a lot that don't go to school because their family wants them to work the field, but a large percentage go to school, but hardly ever past high school. And when they do finish high school, they're often 23, 24, because they've taken years off to work the fields or work construction job in between. So anyway, very different system from what we have here. And throughout that education, the emphasis is on memorization and on the theoretical ideas rather than the practical. And as a very simple example of this, I would have some of these kids that would see me driving up to the hydro plant and would walk along with me. And they learn English. I guess they learn their tribal language, Kinyarwanda, up till about 4th grade, and then English for the rest of their schooling. So these kids knew a little English, and I asked one of them, "Oh, what are you studying?" And he said, "History." And I said, is that Rwandan history or world history? And he said, "History is the study of the past." And so I had to rephrase it for a few different times before he said, "Oh, history of Rwanda." But it's sort of, that was the right answer at school. If you're asked anything about history, you say history is the study of the past. So in that I guess I found that in my staff as well, in that if anything went wrong, thankfully I would get a call about it, but often they would have done sort of what they'd always done and then tell me what I wanted to hear. And sometimes that can be catastrophic when it's not the truth, and you're dealing with $1 million machinery and dangerous currents and things like that could kill people. Anyway, and I also had an employee that I had given her an assignment that was very clearly something she could do. It was in Excel, and she uses Excel every day. But she procrastinated, and when I finally said, I need this by the end of the day, she got really nervous and like, oh, it's a lot of work. And I said, "It's your responsibility." And she said, "Responsibility? Don't say it's my responsibility." So there's an attitude of, I think it's twofold. It's sort of, if you're an employee of someone else, then they have the responsibility, and that's a good thing, and you don't want that responsibility. There's also, if you're the boss, then you've made it, and there's this sort of attitude that I found many times, that you've made it and you're not the one doing the work anymore. So when you put those two together, some things don't get done. Okay, for example, one problem we had was this open canal. Basically every hydro, micro hydro scheme of this design would have a metal rack to keep out all debris from going into that pressurized pipe. So the pressurized pipe goes right here, and before it can go into that pipe, it goes through the rack. before it goes into the rack, this depth increases so that sediment drops to the bottom, because we want to keep the sediment as well as the debris out of the turbine. And the problem with it getting deeper is that this is actually 2 or 3 feet deep. So people can walk in it, people can wash their laundry and things in this, and it's not clear that it gets deeper, and almost no one knew how to swim. So we had someone, we had a man get washed in. He was actually drunk, and he died or like a little bit upstream, falling on the rocks. And I was told he was dead by the time he fell in the canal. But then he was washed into this deep section. We also had a cow that fell in and was washed into the deep section. In response to those, I guess the workers made this, which I'm really proud of them that they made anything for it. But immediately when I saw it, I said, I can't remember if we had issues or if maybe, well, anyway, this was to keep anything from being washed in the deeper section, but there was constantly large debris flowing in. So on a particularly rainy day, this clogged with banana trees, and the whole channel overflowed and eroded that mountainside significantly. And so then I enacted a few countermeasures to say, okay, we'll let it spill over to that side before it gets to the deeper section, and also we'll build a rebar grate so that not so much gets trapped in it and things like that. So you can't really call that civil engineering. You can't really call that any type of engineering. It's just problem solving. The thing is, after working there, I love these solutions. In the dry season, where you still get rain a few times a week, but not enough for our full hydro capacity, we decided to divert a small stream that no one was using into our canal, even though the dam was another kilometer upstream. So this was the initial solution, because this corrugated tin for roofs is very readily available. So just get some forked sticks and bend the tin into the shape of that, and then pile, what you can't see upstream is they piled sandbags and rocks, so that most all of the water went into here while they built a more permanent structure. So I don't know if that's a nice title, because I really love this, but there are no standards, but things get done. So also you can sort of see the level of masonry here, where the space that people will see is very nice and pretty. The space below, who knows what's in that? I know what's in it. It's as much rock as they could put, and as little concrete as they could put for it to still stand. And so that was constantly something I had to push, was like, okay, we need more cement, and we need rebar reinforcing that cement, and not just masonry. And some retaining structures, this was done before I got there, that was nicely done. Sometimes they would build a supporting, what do you even call that? Support, a gabion, something without any aggregate, like with just dry stones piled. And then we knew that people were walking along those and climbing up them. So I said, what if one person pulls off a rock or two? Oh no, they won't. They won't take the rocks, don't worry. So there are a lot of assumptions that go along. And so my job a lot of the time was just encourage, like this was not my design. I told this man in broken Swahili and French what I wanted to happen, and then he designed this diversion structure. So power to him, it works, it's still standing. It's just something that you can't expect. I guess these guys are masons. They do very clean and nice looking work where it's going to be seen, and they're told all their career that where it's not going to be seen, do it as cheaply as possible, and that means use as much local rock as possible. By cultural standard, the rock in a river is actually a communal property, so you don't have to pay anything for rock you get from a river. But if you get rock from a field, you have to pay the owner of that field. So sometimes we'd have the majority of our laborers just pulling rocks out of the river, and then a few of them using the rocks. In general, these were, I guess you had rebel armies, but in general, the job site was a safe place, and people respected power generation. They saw that was a net benefit. But you would still have break-ins and occasional stealing of materials. So this was actually a wire for measuring the height, measuring the depth of water at that pressurized pipe intake. Because if it's too dry and the water goes too low, we can't keep running the turbine at the same level. So we adjust that with a very simple control system using this depth sensor. And someone stole, this was not in my plant, this was in a plant I visited, but they had never actually hooked up the sensor. They had just run piping all up the small metal pipe with wire inside alongside that pressurized water pipe. And local people gradually, I guess it was not being monitored and had never been fully installed. And so some local people found that out and stole the wire and large sections of the metal pipe. This is also a different plant, not mine, but you'd have two doors. I think he had locks on both of these doors, heavy wood, and then rebar with sheet steel welded onto it. Also, his roof was rebar reinforced because he was worried about people coming in from the roof. And then these stone walls were probably 1.5 feet thick. So levels of, I guess, those simple practical security measures we wouldn't worry about here. Problem solving, another example I'll go through quickly. But this was one where I was kind of frustrated because I got the call, you know, they said a plastic piece is shredded. It's broken. I was like, do you have the piece? Oh no, it's in many pieces. And I said, is the turbine turned off? And they said yes. And I drove out to the plant and it was not turned off. It was still running. So I said, turn it off. Don't turn it back on until this is fixed. And basically it was this, the water comes in here and turns the turbine. This is seen from a different angle from before. But there's a butterfly valve that's open and closed by this hydraulic piston. And what opened and closed the hydraulic piston is a motor here that's coupled to a hydraulic pump. And the motor side is here, the hydraulic pump side is here. And so the technician just I brought 1 or 2 plastic pieces, and I went and found some more in there. And he told me this is a four-legged plastic piece. And I thought about it for a while, and I pieced together. The biggest piece I could construct was this, which I think was 3 pieces super glued together, which is a single tooth. And I said, no way do 4 of those teeth fill that. And it was 8. So I basically figured out, like, if this is a tooth and this is a second tooth, then there are 8 going around. And then I found, there were no technical drawings really on the internet, but I found a cross section and made a stencil from printing out different sizes off the internet and trying to match it to this single tooth. And then I took this stencil into our little town and found people that could carve truck tire. And I found the hardest tire I could find, the hardest rubber I could find that they could still work with. And I said, I need you to make me this, of this thickness, and I need it as soon as possible. So this is one of these. I went to a few different places. Didn't have any hardness test or anything. I just had a hammer, and I'd used the hardness tester, so I was like, I know it's something like this, and I could feel which was harder. And eventually, he told me he'd make me one of those for. He really ripped me off, like $12 or something. And so I came back and he had 2, and I said, and he was just going to give me the one that he liked better, that was nicer. I said, can I buy both those? Oh no, I wouldn't. No way. No way. And I said, well, I'll give you $18 for both. Oh, okay. And it fit in, it was perfect. But yeah, basically it's both sides have 4 prongs, and these 8 feet go between the prongs. And turned out we had an associate who was on a business trip in Europe, and so we quickly contacted the company, and we're able to, in a week or 2, get the actual part again. But anyway, you see a lot of innovation, and you meet a lot of these people that are so good at that thing they do. If I knew all those people, I would have no problem building anything you wanted, That's my experience. I know not especially technical, but hopefully gives you an idea of what sort of challenges you can solve and how you do stretch your brain and you learn some about civil and some about mechanical and some about electrical, as well as a lot about policy and funding and international relations and things like that. There's starting to be larger projects in this region. Uganda recently had a 253 megawatt project open. Sadly, in the last 2 years, it started leaking and the machinery started rusting, but it's still operational. This Ethiopian Renaissance Dam, also in East Africa, will be the biggest hydro installation in Africa. There are also huge ones on the western edge of Democratic Republic of Congo, on the Congo River. DRC actually has, I think, 11% of the world's hydro potential. So anyway, this region has so much potential, not just for hydro, but for a region that's sunny, even in the rainy season. You can do so much with PV. There are a few PV startups in Rwanda. Yeah, that's one example, but they've also looked at geothermal around these volcanoes. Geothermal is really successful in Kenya, but in Rwanda they've dug a few dry holes and sunk a lot of money, so they're not hopeful about that. But a lot of room, and the governments are very eager. The governments are writing regulations around what startups are doing. That's something you won't find here. That's something exciting. They're trying to facilitate innovation, facilitate outside money to make these projects happen. They're designing the grid, and in association with outsiders who care. And so that's what my focus is on now, as I'm starting PhD in electrical and computer engineering, and looking at how can we optimally plan grids with the generation sources, and not just say, I guess the minimum spanning tree problem, if any of you are familiar with it, it's graph theory. It was originally formulated for power grids, I think in Moldova, and it was basically saying, if we have multiple, I plotted this on MATLAB, very simple, but basically saying if we have 2 paths from node 1 to node 2, we can choose, what's the minimum cost network to reach all nodes. That's the minimum spanning tree problem. Now, what I want to do soon is an n-1 secure spanning tree, where basically any one line can go down, and you still would have you still would have access to all nodes. N-1 security is not so much done with distribution systems, it's done with transmission systems, but it's a very simple extension of this sort of graph. So that's been done with transmission systems, but it hasn't been done with the generator to say, we could either build PV of 5 megawatts or hydro of 4 megawatts, and we don't need both. I mean, Rwanda, they really don't have the demand right now for all that they've built, and so they're rapidly catching up. So probably in Rwanda we will just build high capacity, but in the world, a lot of places, it might cost an order of magnitude more to make, well, for example, that type of turbine that I had, the half megawatt range we were in was perfect. It was the sweet spot for that type. But if you went up a half megawatt, it would be an order of magnitude more expensive. So you might choose to do half the capacity because it has these other benefits of being simple to install and maintain. You might choose a lower capacity because your dollar per kilowatt is less, and because the demand doesn't require the higher capacity. So basically my research in a broad sense is saying, how can we optimize both the network and the generator when we're planning from scratch. And you don't get that freedom really in the Western world. And then, yeah, hopefully making a model like this that's objective, so you don't just have people that like hydro saying, we're going to build hydro. You don't have people that sell you turbines to say, here's the biggest, most expensive turbine. But you do this, yeah, with the model, let the different players input their data. And then finally defining standards for power generation and transmission. Yeah, I have I've interviewed some folks who had their own private microgrids, and they just were all over the place in sort of the equipment and transmission line thickness and things that we take for granted. I think, yeah, that's all I had to present. I have a few slides just of organizations that you might be interested in. And startups, these aren't probably, I don't know, most of these are not like seeking new help, but it's just an example that startups are forming all the time and there's a lot of space. These are for both hydro and hydro and PV, and I think one or two interested in geothermal. One did a sustainable chicken laying farm and then has moved into hydro and funded one of our hydro projects. So all over the place, you meet very interesting people. And then some funding arms. The plant that I managed was largely funded by a public-private partnership with the German development arm GIZ. So, yeah, I think I already covered this, but small hydro is rapidly becoming big hydro. There's still a lot of space for both. And yeah, all sorts of branches of the energy sector are moving forward. A lot of challenges that'll stretch you. And yeah, a lot of options for who you can work with and how to get funded. Thanks to my advisors and to my funders.
Oh.